back, everyone. So our first speaker of the afternoon is Cheng-Chien Chen from University of Alabama, Birmingham. He did his PhD at Stanford. You were at Argonne,
yes,
right?
Yeah.
And now he's going to talk to us about diagonalizing lattice models. Thanks for joining us, and take it away.
Okay, thank you very much, and good afternoon. So, first of all, I would like to thank the organizing committee for giving me the opportunity to present here. This is my first time attending a PETSc annual meeting. I feel very excited about all the advanced PETSc features and also wide variety of applications. Okay, so I want to begin by thank my collaborators. So today the talk is based on our relatively recent publication in Physical Review B. And so this is done with my former PhD student, Cheng-Chien Chen, who is now at Taiwan Semiconductor Manufacturing Company, TSMC, and also in collaboration with Professor Yao Wang from Emory University. Okay, and the work supported by some mostly NSFDMR and the EBSCO programs. So the calculations I'll be showing are mostly performed on the from Terra supercomputers at TSCC. I also show some benchmark results from a permuter NERSC supercomputer as well. Okay, and finally, I want to thank PETSc and the SLEPc, which made this research possible. Okay. So I'm not an expert in PETSc, SLEPc, so I was a postdoc at Argonne, but I'm not at in ALCF. I was at Advanced Photon Source. So my training was in condensed matter theory, computational materials modeling. Okay, and I learned to use PETSc when I was a postdoc at Argonne. Okay, so for my talk to make sense, I will plan to first of all give a introduction on superconductivity. Okay. And then I'll talk about our solving some relevant model Hamiltonians using exact diagonalization and with our PETSc, SLEPc implementation. And then finally, I think I'll quickly go through the results, okay, and conclude some future plan. So as a motivation, as quantum computers is a very hot topic in recent years. And this is an example showing IBM quantum computers about the size of a person. Okay, but turns out actually the actual quantum processing unit is actually very small. Okay, about the size of your hand, and put at the bottom of this machine. Okay, and the one major use of this relatively big machine is actually to cool down the quantum processing unit to a very low temperature, and we'll see why that is necessary. Okay, so this is a quantum computer based on superconductor. On the right-hand side, just released earlier this year from Microsoft. They called the Majorana 1 qubits. Okay, it's also it's a different type of quantum computers operating on a very different algorithm compared to this IBM 1, but it's also based on a so-called topological superconductivity. So that's let me continue. So what's superconductivity? Okay, so we are familiar with insulator and the metal. Okay, so one definition is actually if you plot the resistivity of the material versus temperature. So for a metal, we expect the resistivity to decrease with decreasing temperature. Okay, so that's the definition of metal. So in 1911, the Cameron-Arnold's group, they decided to lower the temperature of mercury. At a certain critical temperature, about 4.2 Kelvin, they found that the resistivity drops to almost zero abruptly. Okay, so this is the discovery of superconductivity in 1911. Later, we realized that superconductor also has another effect called the Meissner effect, where above these critical temperatures, magnetic fields can penetrate through the material. Okay, however, below the TC, when the material becomes a superconductor, then it actually expels the magnetic fields. Okay, so this is application, for example, in magnetic levitation in the maglev trend, and so this property has application, for example, in energy loss transmission, and also, for example, in quantum information technology as we just saw. Okay. So now, after almost 50 years, we have the first complete theory based on Bardeen-Cooper-Schrieffer that describes our conventional or phonon-mediated superconductor. Okay, so what is that? So we know electron has an intrinsic property called spin. Okay, it can be like, for example, spin up or spin down. So they have a half-integer quantum spin number. It turns out we have two types of particles in the universe. One is called the fermion. So fermion, they don't like to sit in the same state. Okay, so in that case, for any state, each fermion will occupy distinct states, forming so-called Fermi sea, or like a human pyramid. Okay? For superconductivity, we need a both condensation phenomena where we want to have bosons and they all occupy the lowest energy state. Okay, so it turns out you can put two fermions, two electrons on opposite spins to form a boson. Okay, but we know electrons, they have Coulomb repulsion, right? So how do they bond it together? Okay, so one possible way is through a lattice vibration, or we call phonon. Okay, so the idea is that, for example, if I have one electron pass through the positive charge ionic lattice, then it will try to attract the lattice inwards, and after some time delay, then the second electron comes in. You feel the attraction from the lattice, so then effectively these two are bounded together as a Cooper pair. Okay, so this is the mechanism of forming bound electrons to form superconductivity. Okay, but this explains one of the family. Okay, so this is a plot from Wikipedia. Okay, you can check this. So it has the years of the time that each superconductor is discovered versus the critical transition temperature. Okay, so we'll just discuss the mercury, and most of the simple metal on the green can be described by this phonon-mediated BCS superconductivity. Okay, and you can see that this hydrogen-based compound discovered in 2018 actually has a transition temperature of 250 Kelvin, very close to our room temperature. Okay, so unfortunately, you see there's a very large external pressure required to make this material superconducting. Okay, so now for BCS superconductors, the trend is to search for new higher TC superconductors, but without external pressure. Okay. So today we are focusing on this blue branch based on copper oxides. So these are called the cuprates. So without external pressure, these are still the record TC record holder among all the superconductors. Okay. And there's still a debate about what's the underlying mechanism, which is not related to the phonons. Okay. So these are our focus. So what are cuprates? Okay. So these are some crystal structures for different cuprate families. So one common unit is that have a quasi-two-dimensional copper-oxygen plane. Okay, and it is believed that the superconductivity is the key physics is hiding in this plane. Okay, so you need to understand what's going on here. Right-hand side is a common phase diagram for these materials, as a function of temperature and doping hole concentration. Okay, on average, without doping, you have one Hall carrier per copper-oxygen plaquette. And you can introduce more Hall carriers through doping. Okay. Without doping, the thing is actually an antiferromagnetic insulator. So the material from checkerboard spin arrangements. Okay. So this state cannot be explained by, for example, standard first principle calculation or using density functional theory. Okay. That's why we need more advanced calculation that we will introduce shortly. Okay. And if you introduce more Hall carriers, then the system can become superconductors. So the simplest model believed to capture all the key ingredients is called the so-called Haber model. Okay, so for this copper oxygen plane. Okay, this corresponding Hamiltonian operators basically describing the energy. So the first term is a copy of electrons. For example, the Cj sigma is an electron annihilation operator, which will kill electron at lattice site J with spin sigma. Okay, can be up or down. So this C dagger I is a electron creation operator where I create the electron at site I with spin sigma. Okay, and this the Hamiltonian is Hermitian conjugate, so you have to have this term. Okay, the second term describing the interaction. Okay? It says that if you have a lattice site I, you have both spin up and spin down electrons, then you have to pay an energy penalty U. Okay, so this model looks deceptively simple, but actually after 60 years of studies, there's still no exact solutions beyond one spatial dimension. Okay, so so this considered one of the holy grail in condensed matter theory is to solve this Hopper model. Okay. So there's no exact solution. You have to introduce some approximation. Okay, and there are a lot of variety of methods. Okay, so the one we are using is called exact diagonalization. So this has an advantage that it can treat interaction effects exactly, but you are limited to a small size because of the exponential growth of the Hilbert space. Okay. So basically, if you have a finite size lattice with finite number of electrons, and they are fermions, so you have only a finite size possibilities of the electron arrangements. Okay, so this means that solving the Schrödinger equations for our Hamiltonian is equivalent to solving a matrix eigenvalue problem. Okay, and this is where PETSc, SLEPc come into play. Okay. By the way, we are using this Dirac-Kaplan notations. So basically, this is represent a column vector. Okay. So there are a few key steps. I'll go through it, and then I'll show you my implementation. So first of all, you need to choose a basis representation. Okay, for a given lattice and the number of electrons you want. Okay. For example, if you have two-side lattice with one up electrons, then these are possible configurations. Okay, you have a spin up at this side or spin up at the other side. And you can easily use a binary representation and do a bit manipulation to play with the states. Okay, if you have two sides, one up electron, one down electrons, then there are 4 possibilities. And if you have spin up, spin down, these are basically the tensor product of the states. So you can compute the Hilbert space size is Cn, capital N number of sides, choose the number of up electrons, times Cn, choose the number of down electrons. Okay. Of course, this thing will grow up, blow up exponentially. Okay. Once you choose your basis and the numbering scheme, then you can construct the corresponding Hamiltonian for this Hopper model. Okay. For example, for this case, the off-diagonal terms are from the Hopkins. There's no diagonal terms from the U because we have only one electron. Right. For the two electron problem, then you have a Hopper U on the first state and the last state. Okay. Once you set up the matrix, then you diagonalize the matrix to obtain the lowest few energy eigenstates. Okay, so my first step, you need to define a representation, okay, and an ordering scheme. Okay, it turns out this is a very nice paper from Penn State in 1995. It says that actually you have a perfect hashing function to do this. Okay, basically, for example, if you have say you put 2 electron fermions on 5 orbitals. Okay, so this is a C5. Choose 2. You have 10 possible states. These are their corresponding bit representations, and these are their decimal value, integer values for this corresponding representation. Okay, so you can go through this paper in further details. The idea is that there's a one-to-one correspondence, a hashing function that can convert this value to an integer representation from 0 to the Hilbert space size -1. Also importantly, there's an inverse mapping. Okay, give me any number, say 5, then I'll be able to map exactly back to this bit integer representation. Okay, so this greatly facilitates our matrix construction. Okay, and also we don't need to store actually the basis vectors to save some memory because we can compute it directly. Okay, so this is the first step. So now once you set up your Hilbert space, then you start to construct the matrix. Okay, so this is my the way I did it. Maybe far from being optimized, and I welcome any suggestion to further improve the code. Okay, so basically I do first of all a row-wise partition between different threads. Okay, so basically because we have a perfect hashing functions, there's basically no communication at all between different threads. So this part is almost perfectly paralleled. Some little issue I'll discuss because the matrix. This is an example, small size matrix where the blue dots represent the non-zero matrix elements. Okay, so you tend to have more elements towards the center. Okay, so it's not evenly distributed. Okay, but anyway, each CPU is takes care of all your own rows. Okay, then you start to go through all the basic states of your rows. act your Hamiltonian operator on the basic states and try to identify which are possible non-zero off-diagonal elements. Okay, so you do this element by element. It goes through all the rows. Okay. So there's no communication at all at this stage. So once this part is down, then second we'll start to populate the PETSc sparse matrix object. Okay, and we all know that in this case you need to pre-compute the diagonal and off-diagonal elements, number of elements to make the calculation very more efficient. Okay, so this basically you pre-allocate the matrix, you start to go through row by row, set the values, and finally assemble the matrices. Okay, so this is how I did it in the two-step procedure. And if you know a more efficient way, please let me know. Okay, once this is done, then we are ready to diagonalize the matrix. Okay. Again, we don't need the full energy spectrum. We only need the lowest energy states on the order of 10. Okay, and we use a highly efficient Krylov-Shor methods implemented in the SLEPc. I will show you some performance shortly. After you get the states, you can do post-processing to do some expectation value. This basically do a lot of matrix vector products, which you can do without PETSc, but you can also do with PETSc if you like. Okay. So these are the procedure. Okay. So these are the resulting code performance. Okay. This is an example problem on a 20-site half-field Hubbard model. So you have the Hilbert space is C20 choose 10 times C20 choose 10. 10 up electron, 10 down electron. So the Hilbert space size linear dimension is 34.1 billion. And the sparsity, so the number of non-zero elements is roughly 40 times this number. So slightly over 1 trillion non-zero matrix elements. So in that case, I need to store the full matrix. Okay, so these are double precision. And sometimes if you have a complex hopping, then you be a double complex. So 16 bytes per element. I also need to store a few tens of the vectors for my diagonalization. Okay, so eventually we are bounded by the memory. So this is close to the minimum number of memory needed to do the calculations, which is about, I think, a few hundred nodes on Frontera. So Frontera has 56 CPUs per node. This is close to 500 something nodes. So apart from that, you see the code roughly scale more or less linearly. Okay, this is a strong scaling calculations. You fix the same size problem. Achieve about 85% linear scaling compared to this reference point. Okay, and I did the same calculation on NERSC with a similar amount of CPU, get essentially very, very close performance. Okay, so this shows that the PETSc, SLEPc have a very good transferability among different platforms. Okay, so if you have a look at the breakdown, so let's say on NERSC permuter has 128 CPUs per node. So for 480 nodes compared to 880 nodes, sorry, I should make this exactly 2 times of this, but anyway, this is about 1.84 times 480, okay? And I show here a speed up of different sections, okay? First of all, my matrix constructions, these are about 10 seconds. You see the speed up is 1.74. I say there's no communication between the threads, okay? However, this is still not the perfect linear scaling because the matrix, the elements are not evenly distributed. Okay, so the threads close to the ends have less jobs to do, basically. Then I transfer my matrix to the PETSc, assemble the PETSc matrix object. Okay, so this takes about the same amount of time, and this is the speed up. Okay, again, I think this is related to the fact that some threads are dealing with more elements. Okay. And now the SLEPc diagonalization part, which is the most time-consuming part, which is about 234 seconds, 118 seconds, okay? And the speed up is actually larger than the number of the CPU we use, which is 1.84 times, okay? And this is a reason, you can see that there seems to be some fluctuation here, okay? And one of the reasons is that so this Krylov diagonalization, you require an initial guess of the initial vectors. And here we didn't fix the initial vectors. Okay, so it's probably not a fair comparison. Okay, if you want to make a very fair comparison, you probably want to have the same initial Kirchhoff subspace vector and from there. Okay, so this is some fluctuation. But still, it's very impressive that the diagonalization and eigenpair extraction has a very linear scaling, okay, at this scale. Okay, and again, if you have any, so you see this memory is an issue because I want to store the matrix, okay? And this is close to state of the art, basically the largest Hubble model you can do. Also, one possible way to go even much bigger, I feel, is that maybe go to matrix-free algorithms. And if there's any experts in the audience, I would like to collaborate with you on this. I saw there's a talk on matrix-free algorithm tomorrow, so I look forward to it. Okay. And by the way, I got somehow the impression that at this scale, the GPU version is not going to be beneficial. But if I'm wrong, please correct me. I'll look into that. I'm not sure how good it would be if I change everything to GPU implementation at this scale. Okay. Okay, so I'll go through my results. Okay, so the one I just showed you is 20 size, 34 billion. Okay, however, we need to repeat the calculation thousands of times, so we cannot afford to do that 20 size. Okay, so we are restrict ourselves to 16 size problem. So this has a Hilbert space linear dimension about 160 million. Okay, and still a decent size problem, and you do that thousands of times. I'll show you why. Because we have a Hubble model. We also include the nearest neighbor interaction term. So this is the on-site, this is the nearest neighbor interaction. And we are going through the phase diagram for different U and V parameters, okay? Basically, for each parameter, you diagonalize to get the ground state, okay? Sometimes they are degeneracies, so you need to get multiple states. Then from the ground states, we can compute different correlation functions, okay? Again, this is the Dirac-Kaplan notation. This is the column vector, this is the row vectors, and this represents some operator corresponding to some matrices. Okay, so the operator we care about are for example, this pair annihilation operators. Okay, what does this mean? This means that I annihilate two electrons on different lattice size of different spin. Okay, remember we are talking about Cooper pairs for superconductivity, so we are interested in seeing the correlations of this kind of responses. Okay, and turns out if you have a different possible linear superpositions based on the prefactors, okay? Forming different, we call the S wave, P wave, or D wave, okay? So the idea is that if you have a Hubble model with U and V term and the ability to dope the materials, you can induce quantum phase transitions from, for example, a antiferromagnetic insulators to a charge density wave insulators, or to a superconducting states of different pairing symmetry. Okay, so that's the goal. Okay. Okay, so this correlation functions at half field case, and we coupling means a small U and V. Okay, so we first do this test because there are other methods, for example, like a functional remuneration group, which are considered numerically unbiased. And with coupling, we can compare our results too. Okay, so you can see these are correlation function for example, charge density wave, spin density wave, different superconducting order parameters we just discussed: S wave, P wave, D wave, P wave. Okay, so from this we try to extract a phase diagram of U versus V for different possible phases. Okay. So this region called phase separation means that the particle becomes Hall rich and the Hall deficient regions, so they are irrelevant for our calculation. So we focus on this region. So there's always a question because a phase transition occurs only in thermodynamic limit. Okay, so we are at very small size classes. How do you know you have a phase transition? Okay, so one possibility is to compute so-called fidelity matrix. It's basically a overlap, a dot product between of a row and a column vectors with slightly different interaction parameter. Okay, so the idea is that if two states are very close in energy, then so in nature, then this fidelity is large. If you have a distinct nature of the states, then there will be a substantial drop of the fidelity. Okay, and you can see if we go through these transition boundaries, you see that one drop, two drop indicate two-phase transition. if you go through this boundary, and you will see 1, 2, 3 drops indicate 3 phase transition boundaries. Okay. Another thing you can do, which I'll skip the details. We can also do a quantum quench of the material, and we know how to evolve our state based on this time evolution operator. Okay, so this is the matrix exponential operators, which you don't need to know the computer full matrix is very complicated. Okay, however, if you just do the matrix acting on a vectors, this we know how to do it. It's at a much less effort as implemented with again using the PETSc grid subspace methods. So you can compute the time evolution and do a Fourier transformation to obtain the spectrums, and you will see that these different spaces have a different excitation spectrum. Okay, so these are relevant to cold atom experiments. You can actually directly measure in experiments. Okay, then let me show. This is the strong coupling phase diagram. Let me skip to the probably more important results. So at a very large Hall doping concentrations, we found that there's a substantial enhancement of so-called P-wave superconductivity. Okay, so this is important that if you have a chiral P-wave superconductors, it can host a topological non-trivial quasi-particles relevant for this topological quantum computation. That's why people spend a lot of time trying to identify, for example, P-wave superconductivity. Okay, so our results show that if you have around this region U equals to 8, and the V versus around -1, they have substantial enhancement of the P-wave superconductivity. Okay, and this is exactly the parameter regime relevant for cuprate superconductors. Okay, by the way, so just 1 minute. We are repeating the similar results on a hyperbolic lattices. Okay, so which can be now realized on a circuit quantum electrodynamics for superconducting platforms. So this is ongoing research. And be interesting to, so they have a lot of efforts to try to solve a Hubble model on quantum computers. Okay, so these are close to state of the art, 16 to 20 qubits. And actually, we need 2 qubits to represent one fermion. Okay, because there are 4 possible states. So this will correspond to like an 8-side problem, which is about 1,000, a linear dimension, a matrix of linear dimension about 1,000. So this is still far away from what we are doing with classical supercomputers. Okay. However, there's a chance that you might be able to use that to prepare our initial grid of subspace vectors. Okay, to conclude, thanks to PETSc and SLEPc, we have a highly efficient exact direction code for the Hubble models. We identify a potential P-wave superconductivity close to this regime. Okay, so this has to motivate. So this paper. Since population has acquired about 30 citations right now, which is not bad for a PIB in 2 years. So there's motivate lots of Monte Carlo and density matrix relational group studies on whether there's a P-wave superconductivity. Okay, and hopefully, if we can do a much slightly bigger systems with a matrix-free algorithms, then we can say more about this. Okay, I'll stop here. Thank you very much. Yeah.
So I know we have lots of people who would like to try to help with, accelerating performance and going matrix-free. Maybe we can use some of the time after the talks, but let me see if there's another question, Matt.
So I'm interested in this hyperbolic lattice models.
Yep.
How are you doing the quantum on curved manifolds? Is it like Reggie calculus or?
Yeah. So basically. Very brief. So what I just showed you is on a flat Euclidean space. Okay. So there are only possible way to tile lattices, a triangle, squares, or hexagon. So on a curved hyperbolic lattice, you have infinite number of ways to tile the lattice. Yeah. So the unit cell is infinitely large. Okay. You can identify a small unit cell. So this is so-called Poincare representation. You do a conformal mapping of your lattice site onto this unit disk. So you can each crossing is a lattice site on this disk. Okay. So what we can do is we can choose some lattice with 16 or 24 sites, and do exactly what we have done on the Hubble model on this lattice. So now you have different neighbors, different topology. Yeah.
Oh, but you don't. But there's no difference in it. There's no interaction distance measure. It's just the nearest neighbor spin. Right.
Yeah, you can consider longer range interaction or cross-funding.
So the topology is all included in the interaction number, basically.
Yeah, exactly. But also on the how large the lattice you can treat.
Oh, okay.
Yeah. Okay.
Yeah.
And this can actually be realized nowadays. Okay. So these are we just got the ground state energies and the ground state eigenvectors we can do further. So the problem here is actually now you have start to have non-abelian because here the translation along x and y they no longer commute. Okay. Yeah. So it turns out you have non-abelian statistics. So our order parameters are much more complicated. Okay. We have like close to 100 possibilities. Okay. So but this is something interesting. Okay. Great.
Cheng-Chien, thanks so much for your talk.
Okay. Thank you so much. Yeah.